Hi class, I want to go over certain rules that I think are pertinent for this particular course specifically, since it's so heavy duty on writing mechanisms and looking at the reaction conditions and predicting products. I'm going to call this video Writing Mechanisms Right, and I'm going to go over 10 rules which hopefully if you follow you would get your mechanism right and not make errors as you go through drawing the intermediates towards that particular mechanism. The first rule that I want to talk about is that arrows are used to indicate movement of electrons. So whenever you're showing an arrow, and let's say you write it as a double-headed arrow, that signifies movement of two electrons. Likewise, if you have the fishhook arrow, which is a single-headed arrow, that will signify movement of only one electron. So whenever you're looking at movement of electrons or attack of one species over another, essentially it's the movement of electrons, and the double-headed arrow tells you that two electrons are moving. Recall from class that electrons always move from source to sink. What that means is that if you have a nucleophile which is rich in electrons, that means it's a negatively charged species or has a lone pair of electrons that can be donated, only those can act as sources. And where would they move to? They would always move towards the positively charged species, towards the more electron deficient species. So let's take a minute to talk about the electrophile and the nucleophile. Just a very quick recap. Over here I'm showing you two species which are electron sources. One is neutral, that means it has no charge. And that's ammonia, and it does have a lone pair of electrons. Another has a negative charge, and that's the hydride anion. So these will be called as nucleophiles because these are electron rich in nature. Likewise, BH3 and H+, these will be called as electrophiles, and the reason why I'm calling them electrophiles is because they have a love for electrons. That means they themselves are electron deficient. So if you think about H+, that of course does not even have, it's a single proton, it does not even have the single electron that is otherwise present in a hydrogen atom. If you think about BH3 and write down the Lewis structure of BH3, recall boron has 3 valence electrons. So again, whenever you're in doubt, always write down the Lewis structure. 3 electrons come from boron, 3 electrons will come from hydrogen because we have 3 hydrogen atoms. So total you have 6 electrons. You wanted it to be an octet, but it is no more than 6 electrons. That means this is electron deficient. It's a Lewis acid. Various ways to say the same thing, and hence it will accept electrons readily from any species that is willing to give those electrons. So ammonia can donate electrons to boron, and it will form an H3, electrons going to boron. That's an adduct that you get. NH3 will now have the positive charge. BH3 will have the negative charge because it has accepted those electrons. Likewise, NH3 can donate electrons to H plus and give you ammonium ion. Notice the positive charge on the left side of the reaction and the right side of the reaction is the same. Electrons are moving from source of electron, which is ammonia, to sink of electron, which is H plus. Likewise, you could write down the same kind of electronic movement with hydride. So let's take a look at that. We have H minus, and if that is treated with BH3, again electrons will come from source to sink, and you will get your BH4 with a negative sign. So electrons again are shown in a mechanism, the movement of electrons is shown using arrows. It always is from source to sink, never from positive to negative, always negative to positive, N to P, always. Okay, let's talk about rule number 2. What do these arrows signify? These arrows indicate the movement of atoms indirectly to basically show the covalent bonds broken or made. So you might think in your head, for instance, that this hydrogen is kind of coming together with boron, but really it's the electrons that are participating in the bond breaking and the bond formation. So just kind of keep that not on the back burner, but kind of in the front burner, that those bonds are being broken and bonds are being formed by the movement of electrons. It might seem that you are moving atoms, but it's kind of like an indirect placement because these electrons are a part of those atoms, really. All right, so in that sense, my rule number 3, that arrows always move from electron source to sink. We've talked about that now. Realize that you never want to have an adduct or a transition state which is hypervalent. What that means is that you would rather break a bond rather than overfilling the valence space. So when you're showing the electronic movement, just keep an eye on the fact that you have to follow the valency. For instance, if you have carbon can make only 4 bonds. Nitrogen, it has 5 electrons of its own. It needs to make only 3 electrons. Likewise, oxygen, it has 6 electrons. It needs to make only 2. Fluorine, likewise, has 7 electrons and needs to make only 1 bond. Boron, like I said, always it's a Lewis acid. It makes less than what it is supposed to because it doesn't have those many electrons. But keep an eye on the number of bonds that you're making. That means if you find yourself drawing 5 or worse 6 bonds to carbon, for instance, be on the lookout. Check again. That's a red flag right there. The way you have shown your bonds is not accurate, and you need to take a hard look at the mechanism that you're writing one more time. Another thing that I would very strongly recommend is that when you are making bonds or breaking bonds, expect to form relatively stable chemical molecules. I mean, recall from the energetics that we talked about, potential energy on the y-axis, reaction progress on the x. You have, let's say, A going to B. You always try to get, let's say it's a 2-step process. You always want to get that intermediate, which is relatively stable. You don't want to form something which is unstable. So for instance, if you had the choice to make perhaps a primary carbocation versus a tertiary carbocation, it's a tertiary that is going to get formed because energetically that is a more favored process. That is the one which is going to have a low energy intermediate and a low energy transition state in that particular case as well. So recall the kinetic and the thermodynamics and also the stability of your intermediate when you are trying to pick one intermediate over the other. Now, Rule 6 states that a proton exchange will take place when there aren't suitable nucleophiles or nucleophiles, but or electrophiles, but the electron has a strongly basic functional group or has an acidic proton. What that means is that if you have, let's say you're using T-butoxide. So recall from chapter 11, which was about substitution and elimination reactions. This molecule is a bad nucleophile. It's a poor nucleophile. And this is not the only one. You can think about triethylamine, for instance, which is a weak base, and it is a bad nucleophile. The T-butoxide is a good base, but a bad nucleophile. It's a bad nucleophile because it's bulky. So you have a very big bulky group attached to the oxygen with a negative charge, but you call it a good base, a fairly a good base because of the negative charge. In case of triethylamine, you have a lone pair, you have no negative charge there, and the ethyl group makes it bulky, so it's a bad nucleophile in that sense. But whenever you have something which is a good or relatively good basic conditions, and there is an acidic proton. So this is the conditions where your conditions are basic, right? Or you have an acidic proton. What will be an acidic proton? Recall the acidity that we discussed in chapter 2 about acids and bases, the cardio. What are the reasons, what are the things that make something acidic. So just to kind of give you a flavor for if you have a hydrogen which is pretty close to an electronegative element or a positive charge. What I mean by that is you have a hydrogen at the beta position of something, for something that will pull electrons. So let's say you have something like this. So you have two hydrogens here. This is alpha to the bromine, and if you subject this to T-butoxide reaction conditions, which are basic conditions, that T-butoxide would want to pull the proton off, electrons will move, bromine will go away. What does that tell you? That tells you basically a couple things. Bonds are breaking. The bonds that are breaking are the bond between carbon and hydrogen, and in turn those electrons are moving in between the two carbons. Let me change the color in between these two carbons. And in that process, again, the electrons between the alpha carbon and the bromine, they are going away with bromine as a bromide. And so your end game, your end product is an elimination product, and you get your double bond in place. Rule 7 is polarity. So it says follow polarity. And that basically means that the negative is going to interact with the positive. The positive is going to interact with the negative part of the molecule. So if you have, while writing mechanisms, and we are going to actually discuss carbonyl compounds in good detail, but let's say, just to give you a flavor for what's going on, let's say you have a aldehyde. Now you know oxygen is electronegative, so we have negative charge over here because of the pull of the electrons towards oxygen. That renders this carbon slightly positive, so that is electropositive. And let's say I treat that with something called as a Grignard reagent, and we'll discuss what a Grignard reagent is. I am not sure if everybody is familiar with that, but Grignard reagent is an organometallic compound where you have a metal connected to the carbon atom. So you can hopefully see metal being on the left side of the periodic table is going to be the more positive end, and your carbon is the one which has your negative end. And so what that means is that when the reaction takes place, since it's negative to positive, the negative on the carbon is going to attack the carbon of the carbonyl, the electrophilic carbon, and the negative of the oxygen is going to pick the magnesium. So those are the two kind of interactions that are going to occur. So if somebody asks you what is that first arrow that you would want to show, always N goes to positive, negative goes to positive is what you're going to say. All right. Rule 8 is that you cannot show creation of protons or positive charges if your reaction conditions is those are basic in nature. That means if reaction conditions are basic, all you can have in that reaction mix is something neutral or something negatively charged. Likewise, if the reaction conditions are acidic, you cannot have a negative charge there. You will have to show everything positive or neutral. So what I mean by that is, the reason why I say this is, let's say you have like a acidic condition. That means you have boatload of protons around. What that means is any source of electrons, such as a negative charge, is going to get protonated very, very quickly. So whenever you're trying to identify your reaction condition, whenever you have lots of acid in the reaction mix, you will not draw intermediates with negative charges. Likewise, when you have a basic reaction condition, you will not draw positive charges. That positive charge would lose that charge very easily, very quickly. And as you're going through the transition states, I mean, some of this is kind of common sense, but again, you want to always keep your octet intact. So always follow the Lewis theory and always keep your octet intact. That's an important one. The last rule is, if an intermediate can be stabilized by resonance, that is the most probable way of stability. So I've said that before. My favorite word, resonance, is for a reason, because resonance exists to stabilize a certain molecule, and in doing so you release a gigantic amount of energy called as resonance energy. And since it's a thermodynamic way of going about things, that is what is going to take place. Energetically, molecule always occurs or takes the route, the molecular interactions always occur, they take the route so as to follow the more thermodynamic route, which basically means lower the energy, and that's a good thing. And that was rule 10. What I'm going to do now is give you an example, something that you have never seen before, but we are going to try to apply, things to make sure that we understand what's going on. Okay, so what you're seeing is Swern oxidation. I have given you the steps and I have given you some information, and of course if it was a word problem then everything would be written in words, so it's your job to read the question. But I'll just run through the whole thing with you. So what you have is dimethyl sulfoxide, or DMSO as it's called. Recall that's you first heard about it in chapter 11 in organic 1, that it's an polar aprotic solvent, and usually that's used to facilitate SN2 reactions. Here it's going to serve a different feature altogether though. And we are treating that with oxal chloride, so that's the species right over here. Now you have to put some electrons and you have to show how the reaction is going to proceed. So we'll take a look at that. Now, before you make up your mind, as to how the electrons are going to kind of move around, you first should see where the electrons reside. So that's your rule where it talks about follow polarity. So you have to first look for where the negative is, where the positive is. Notice between oxygen and sulfur, oxygen is more electronegative, so that is the one that's going to have slight negative charge. Sulfur, on the other hand, is going to have a slight positive charge. Likewise, when you think about the oxalyl chloride, oxygen is going to have your negative charge, carbon is going to have your positive charge, and in turn, you have two Cls. What do I know about Cls? Cl is a good leaving group. And why is it a good leaving group? Recall from Organic 1, it's a good leaving group because when you put a proton next to a Cl, and I really should have put that on the left hand side so it looks like HCl. HCl, the conjugate acid of the Cl negative, is a good acid. That is why Cl negative is a good leaving group. So in a situation like this, where you have two methyls and they are not good leaving groups, those are going to stay there. When you add a proton to the methyl, that's going to give you methane, and methane is not acidic. So in this particular situation, hopefully you can see that it's the negative charge on oxygen which is going to be nucleophilic, and that is going to attack the positive electrophilic carbon. So the way the reaction will proceed is you will show the negative charge attack the carbon, and it is going to force the electrons to go on top of oxygen. So your first step, anytime you're writing a mechanism, always keep just 2 to 3 arrows in one step. Don't try to push all arrows, kind of together. Don't do that. So when that happens, what are you going to see? You're going to end up with sulfur with a positive charge, 2-methyl still intact, oxygen, and now what is oxygen bonded to? Oxygen is bonded to carbon, which has the negative charge, Cl. I'm going to number that just so you can follow along. So that's my carbon number 1, and the COCl still intact. Notice as the bonds got formed, carbon is still forming 4 bonds, oxygen still has 2 bonds. Sulfur, if you think about it, it has 6 electrons around it right now, and so it should have a positive charge. So everything from the perspective of Lewis structure makes sense. The oxygen has a negative charge because it forms only one single bond in this particular structure. So what can happen now? That negative charge is going to come back in between carbon and oxygen and force the Cl to leave. As that happens, you're going to see oxygen, double bond O, CO, Cl, positive charge still intact. What can happen next? So this is probably your first intermediate that you're going to end up with. That sulfur is going to hold that positive charge. Now, this next step basically tells you, it gives you information that 3 molecules or ions are going to leave. So anytime on the arrow you see a negative, that tells you that these are going to leave. So you can either put it that way or you can put it plus something, something, something. 2 ways to write the same thing. So 3 such species are going to leave. So you have to look for good leaving groups, and good leaving groups would either be something that is gaseous in nature. So that will be a good leaving group because according to the Le Chatelier principle, it's going to move in a direction to undo that effect, and that means that it's going to move towards the product. So that will be a good leaving group from the perspective of formation of the product. So what can happen next? Let's take a look. Your Cl negative, which had left, is going to come back in. It's going to attack the positive charge. These electrons, which are between oxygen and sulfur, are now going to move between oxygen and carbon. That should break the bond between carbon and carbon, and when that happens, one of the Cl's will leave. So your 3 molecules that will go away will be CO2, carbon monoxide, and Cl negative, and what will remain is this species. So you have 2 species, one species that just got generated, and CO2, CO, and Cl negative, those 3 will leave this intermediate. And now it's time for that newly formed intermediate to react with the alcohol. Notice that my sulfur still has the positive charge because it only has 6 electrons around it. Now, also notice that oxygen in this case is the one that has electrons, so that's nucleophilic, and sulfur is going to be the good electrophile because it contains the positive charge. So you can show an attack from oxygen to sulfur, and in that process essentially Cl can be lost, and when that happens, let me make some room. When that happens, you will get a new species that will look like R. Oxygen is my source of electrons, and it's forming 3 bonds right now, so that will give it a positive charge. Bond is going to go on sulfur, and now in the process, the Cl that was gone is going to pick up that hydrogen essentially. So maybe let's show it this way. So you're going to see you have R, oxygen, hydrogen, and you have sulfur, Cl. A simpler way to show that would be that these electrons attack Cle. So it's kind of like an SN2 type of a reaction mechanism, and that will give you your alkoxy sulfonium ion. So our oxygen, sulfur, 2-methyl still there, positive charge because Cl has gone, and HCl would be lost, so minus HCl. Or if you wanted to write it as a product, then HCl. And now we have to treat it with triethylamine and see what happens when you treat it with a base. So that's the last step essentially, and I'll have to erase some things to make room for this. Now if you think about it, and I'm about to use another rule as to which proton is going to be most acidic, and the answer to that is the proton that is very close to something which is positively charged. So what's going to happen is that the triethylamine is going to pick up the proton and leave a negative charge on the carbon. So that gives you the carbon ion, CH2 with a negative, and that then is going to pick up the protons now that are next to the carbonyl, so that these electrons are going to move, and then the sulfur oxygen bond is going to break. So what you're going to end up with is R C double bond O, so there's an oxidation going from single bond to double bond, and sulfur with 2 methyl groups, so dimethyl sulfide. So dimethyl sulfoxide underwent reduction and gave you dimethyl sulfide, and the alcohol gave you the corresponding carbonyl, hence the transfer of the oxygen atom. Hence you can say that yes, this is a type of a redox reaction.